This is a video from Module 5B on pulsars. Stars have magnetic fields. If you compress this to the size of a city, the magnetic field strength grows exponentially. This is the case for neutron stars, which occur when high-mass stars die. Neutron stars are tiny, only about 20 kilometers in diameter, which is approximately the size of a city. When a neutron star's magnetic field and rotation are not aligned, it creates a pulse made of charged particles stored at the base of the magnetic field. This releases what we call curvature radiation and results in a beam of radiation. If this beam intersects our solar system, we see every time the radiation is pointed our way. This occurs when a neutron star rotates, and it creates what we call a pulse, and is why we call neutron stars pulsars. So you can see on this image, here are the beams of radiation, the magnetic fields, and the neutron star. In this module, we will try to detect this pulse and the period of that pulse. The pulsar I chose to study is pulsar 1919 plus 21. I used Green Bank Observatory's 20-meter L-band receiver, which detects radio waves with frequencies between 1,300 MHz and 1,800 MHz. I used the low spectral resolution mode and the HI bandpass filter. This filter narrows the detector's response to only 1,355 to 1,435 MHz. It also removes frequencies that are known to have a lot of human-made interference. Unlike most of our observing experiences, here we're not trying to make a picture. We simply wanted to point the telescope at the pulsar and collect data points using radio frequencies. So I selected the track path and set the duration to 180 seconds and set the integration time to 0.021 seconds. Here you can see the data inside of our software, Astromancer. As you can see, it's super busy. And that's what makes this pulsar challenging, because it isn't always pulsating at full strength. Even if I zoom this data in, it's still super messy and doesn't make much sense. This initial page is what we call a light curve and plots brightness against time to find the pulses. And here I will play the original audio file of those pulses. As you can tell, it is super noisy and you can't make anything of it. Our job in this module is to try to find a pulse so that audio file you can hear the beam of radiation hitting the telescope. This next slide is called a periodogram, and it allows us to refine our pulse points. Typically, you want to find the rightmost peak and ignore the noise. However, what makes 1919 plus 21 so difficult is that they are one and the same. As you can see in this periodogram, the highest, most right peaks are also super noisy. It's hard to tell what's what. So our job is to refine that. My first test observation or test period is the rightmost and highest peak right here, which is the purple polarization double Y peak. I estimate that this is occurring at about 1.85 seconds. Based on this, I changed the background scale on our data to 1.9 on the light curve to help with this subtraction. As you saw on the last slide, this background scale, change it to 1.9 to help refine the data. I also plotted 2,000 points instead of 1,000 points on the periodogram. I changed the start period to 1.85 seconds. The end period kept it at 2 seconds. As you can see here, this is what we're end up with, and this purple curve right here is the same as this peak right here. Once we found this peak, or I found this peak, I used it to obtain our first test period where this peak is occurring at, and it is about, or exactly, 1.8611 seconds. So I took this and I put it into the period folding page, which takes our original data and chops it up every period to try to clean up the data and refine the audio, which you can see on this next slide. still not making much sense. And if we play the audio after it was quote unquote cleaned up, is what we were left with. You can kind of make something out in that, but it's still super noisy. And you'd really struggle to use that for anything. So clearly this was the wrong period. And I tried many, many more periods to try to refine this with no luck. And after speaking to my TA Harshal, we decided to chalk it up to a failed detection of pulsar 1919 plus 21.